All right, I do a couple more videos for you for physics. So, gravity. Okay, I'm sure Ford talked to you guys in chemistry about this. So, gravity is one of the least strong forces in the world, in the universe. But the force of gravity, the universal constant is this. The force of gravity is big G, big M, little m over r squared. What do I mean by that? Simply means that there is some gravitational force, and it is proportional to, this is just a proportionality constant. Not unlike a slope, by the way. This is the distance between them, their centers. And then the mass of the two objects. Masses. Nice. Doesn't matter who's which. Okay. Typically, you're going to have one bigger than the other one because the one's orbiting the other one, but whatever. So, whatever. So let's say here we are. There's the sun. Yay. Whoa, there we are. Whoa, out here somewhere. Earth. All right. The rock from the sun. Anyway, so you can find the gravitational force needed to keep us in orbit. Okay, so F equals, and so big G is 6.67 times 10 to the minus 11. I thought I almost messed it up. 6.7 times 10 to the minus 11. In other words, 0.000000, whatever, 67. 67. Anyway, whatever. So the mass of the sun is what? 6e30, I believe. Yes. Well, no, where did it go? 6e30, I thought. Didn't I just look that up? I thought I wrote it down. One moment, please. I have to giggle it. Well, I have to look up in the back of the book. Oh, the mass of the sun. It doesn't say. Well, by God, we're going to solve for it. Yay! So, okay, now hold that thought. You're like, Groom, can we actually solve for it? Well, of course we can solve for it. Let's say we know the mass of the Earth is, 6.4 E6. Oh, it's not, you dumbass. It's 6, 10. Hey, it's 6 times 10 to the 24. 6 times 10 to the 24. There it is. Perfect. And then, right. And then, of course, we are 93 million miles away, which is 1.6. What is it? 1. Yeah, gummit. Be nice, Jay, if you just write some stuff down before you just start. Whatever. I feel like. Anyway, let's giggle it. 93 million miles, 1 AU, 1 astronomical unit. There it is, baby. I need that baby in meters, thanks. Yeah, 1.49 times 10 to the 11. 1.49 E11 squared. You with me? And then, what is the force? What is the force, Groom? Well, that's a good question. So, think about this for a minute. What actually keeps us in orbit? Gravity does. I thought it was centripetal force. Bro, centripetal force is never really just centripetal force. You with me? It is something else doing it. So, you're on a string being spun around a circle. Okay, it's tension is providing the centripetal force. Okay? Going around a corner, provided you make it around a corner, it's friction. Okay? Here in this case, it's gravity. So, gravity is equal to centripetal force, yes? Centripetal force, mv squared over r. And you're like, well, that's exciting, I guess, except for, which m's which, Groom? Good question, right? So, m is our mass. Yeah, that's going to cancel out. Sure is. 1.49 E11. Hey, that's going to cancel kind of too. I know, totally. And then we need to know how fast we're going in meters per second, roughly speaking. Okay? So if we do this, okay, 1.49 E11. Let's copy that thing. Copy. Can I copy? Will you let me copy? Thank you. And then let's go and let's paste that thing. Paste. That a babe. Times 2 pi, right? Right. So that's the circumference of our orbit divided by 365. Well, shoot. Divided by 365 times 24 times 60 times 60. That will give us the meters per second. So we're going roughly, 29,790 meters per second. 29,790. Oops. Poop. Oh, poop. 29,790 meters per second, of course, squared. Okay? Now you're like, so what can cancel? Right? And I'm going to multiply this guy to the other side. So this is going to end up on top. 1.49 E11. Right? And then I got to divide by 6.7 E minus 11. Hey, that's going to make it big. Well, it sure is. It sure is. Nice. Now, you do this. You can do the math on this. Sorry, that's going to equal to the mass of this thing. And so the mass of the sun is fairly large. I want to say it's E30 in that ballpark. And so, yeah, something like that. So 29,790. Oops. Squared. Times 1.49 E11 divided by 6.7 E minus 11 is, I didn't screw it up. Hey, how about that? 1.2, it's about 2 E30 kilograms, which is the mass of the sun roughly. Yay, we did it. Woohoo! Could you do the same thing on Earth, for instance? Of course you could. So we know that mg is the force of gravity on Earth. We call that weight. And what is that? Well, it's big G, big M, little e, m over r squared. Hey, this is the whatever you dropped. Apple. Your book, I think, uses an apple. But you could just as easily have used something else, car, whatever it is. It won't matter. It'll cancel out anyway. So that's gr squared over big G. This would be the mass of the Earth, or the mass of whatever planet you happen to be standing on, good sir. So that'd be 9.8 times 6.4 E6. Oops, should be times, dumbass. Oh, poop. 9.8 times, parentheses, 6.4 E6. Yay, there's 6E24, and that's how you could find the mass of the Earth. Woohoo! Lots of cool stuff like that that a guy could, in fact, do. Nice. One moment, please. Okay, what I always do with the kids in class, I'll do it for you as well. Part of it's done in the book, but I don't know if they do a very good job of it. If you put a satellite up in orbit, and you want to be over this part of the Earth always, and that is they stay on locked to one another. We call this a geostationary orbit. It's always overhead. We don't see it move at all. It always stays right over us. Obviously good for communications because obviously it's always over one area. It's kind of neat. Okay, so that's kind of fun, kind of cool, whatever. Well, here's the deal. We need to know this height right here, right? That's what we need to know. Okay. But what I do know is that that is some r plus h is the whole thing. And this is just r down here, right? So we're going to solve for h, if you will. Now, what do we know here? Well, we know they take the same amount of time to go all the way around. It takes the same amount of time to go here as it does to go here. So who's going faster? Well, the outside guy, obviously, because he's got a lot farther to go, correct? Well, how do we do that? Well, we know that mv squared over r is what we're talking about, right? It's v squared over r kind of situation, okay? And so you can kind of think of that from that standpoint, okay? And kind of get at it from that standpoint there as well. You can think of it that way. But think about it this way, I guess, more than likely. So here's the distance here. This is distance. The distance for this guy would be equal to 2r plus h times pi, right? Right? And then divided by a certain amount of time, 1 day, for instance. It won't matter because on the other side, what are you going to end up with? You end up with the same thing on the other side as well, if you want to think of it from that standpoint. And so this is, when I look at this problem here, this is the distance. This is how fast, that's how far they went. This is divided by time. And so we know these two velocities have to be the same. And so this is r, 2 pi r is equal, or over t is equal to that. Okay? And so when you do the math on this guy, it actually comes out kind of slick. But then you're like, but Grim, how does that work when it comes to, so we know these two velocities, we know these velocities are not the same, but the times are the same. Does that make sense? So we can't, like we'd like to take this guy here, we'd like to set this velocity equal to this velocity. That's not true. We know this time is the same for both. Yes? What we know is that 2r plus h times pi over its velocity is equal to time is equal to 2 pi r h, or 2 pi r, I mean, divided by his velocity. Velocity 2, velocity, whatever, okay? We know that's what's equal. So it's interesting to think of that, but you can't do it that way, okay? But what you can do is we can actually talk about, hey, so if you're a point here, are you experiencing centripetal acceleration? You are. And if you're the point out there, are you experiencing centripetal acceleration? Yes, you are. Is that caused by gravity? Yes, it sure is. And so we're going to just take a look at this real quick. And so we know the velocity that you need for a critical value to stay in orbit is equal to the square root of rg. Right? We know that to be true. Okay? So when you are in, low Earth orbit, that's what's true. And then when you do this, of course, that becomes this. So this is on the planet, right? If I'm spinning around, I know what g is. G is 9.8. But out in space, I have no idea what g is. So I actually have to use the force of, or the acceleration of gravity out there. And so to do that, what I'm going to get is it's r e squared, or just r for us, okay, times g naught, which is at the Earth's surface, divided by, and then divided by r, which is its actual height, okay? So we're going to call re and re, and then this they're going to refer to as r. This is the way the book kind of looks at it from that standpoint. Okay, doesn't really make any difference, but there it is. So then, okay, what do you got? Well, that's your velocity, right? Okay, that's my velocity. And so we know that's what it has to be if you're circling over us at some point, right? So that's easy enough. So again, 2 pi r over t, and then we're gonna use their definition of r is the r plus h, re plus h. Okay, there you go. Nice. So we know that thing right there, that's a velocity. It has to equal this thing here, re squared g naught over r. Okay? And so if you square both sides, you're going to get 4 pi squared r squared over t squared is equal to re squared g naught over r. Okay, what are we solving for? We're solving for t. So first things first, lose an r. You with me? Okay. And then we're going to go 4 pi squared r squared. Nope, already lost the r. Sorry, I lost the r. I just lost it. Divided by re squared g naught is equal to t squared. Okay. So you look at that problem, you're like, oh, okay, that's doable, I guess. It's easy enough. So if I do that, oh, wait a minute. Did I really do that? Did I really just do that? Did I really just do that? That's embarrassing. That should be cubed, sorry. There you go. And the reason it should be cubed, by the way, is you can actually see Kepler's law of motion in here, by the way. Can you see it? t squared over r cubed is equal to a constant. This is equal to re squared g naught. All those are constants. And that is actually Newton's law, Newton's third law, by the way. But anyway, there it is. I should have caught myself on that. I apologize. And then we simply square root that thing. Okay? And so if you plug all the math into that thing, sorry, what am I doing? I don't want to solve for t. I want to solve for r cubed. God have mercy. You know what? It'd be nice if I wasn't stupid. Let's try that again. Well, we're not going to try it again. We're just going to get what we want to solve for. I forgot what we were going for. I was going for t. Hey, what is t squared? Well, it's some time frame. What time frame? Well, I guess of a day, but it could be any time frame, I guess. Well, then why would I solve for it? That's an excellent question. Why would you solve for it? But okay, so there it is. So we're going to do it in seconds because obviously it is 1 day worth of time. That's what we're going to actually look at. And so it's pretty straightforward. So in our situation here, we would have t squared would be 86,400 seconds in a day squared times 6.4 E6. That's the mass of the Earth. Squared times 9.8 divided by parentheses 4 pi squared. And you get 7.6 E22 roughly. Okay, meters. And you're like, that's it. That's not it, sir. Because it turns out it's quite a ways to the center of the Earth, yes? So we need to minus from that 6.4 E6 meters. And so, minus 6.4 E6, and that's 64, dumbass. There you go. And it turns out it's 7.59 roughly E22. Still about, okay, meters, and which is roughly, what is that? My, damn it. What? Okay, I can't run a cat. Oh, I didn't cube root it, you idiots. Why didn't you catch me on that? J, to the 1/3 power. Yay, there it is. Okay, minus 6.4 E6. And you get that thing right there. 35940, 35940, 39 meters. Or about 22,000 miles. Give or take. Okay, that is where you would place your geostationary satellite so that it would always be over the same part of the Earth. Apologize for that. I got to pull my head out of my butt. As I said before, if you come right here and look at it, you end up with r cubed over t squared. That is, the radius cubed over the period squared is equal to a constant. Okay? Now, specifically for any satellite around the Earth, it's that constant. Okay? Any satellite around the Earth. And you're like, like what? Like the moon? Yeah, like the moon. Let's do the moon, bro. Well, what would you do? Well, okay, let's find out. Okay, so again, here it is. This is the moon. Okay, so the moon, it's for the Earth stuff. So let's plug it in. So the Earth stuff is 6.4 squared, 6.4 E6 squared times 9.8 over 4 pi squared, whatever that number is equal to r cubed over t squared. So I'm going to tell you right now that the moon is, let's look it up. I don't know what I was going to tell you, and I don't remember what it is. So distance to the moon meters There you go. Come on, baby. 384 million. 384 million. So 384 384, 1, 2, 3, 1, 2, 3, cubed over t squared is equal to this thing. Now, let me get you that thing right there. So, parentheses, 6.4e6 squared times 9.8 divided by parentheses 4 pi squared. No. 4 pi squared. Comes out to be that god-awful number. You know what I mean? 1.016, 1.016 E13 or something. Is that what I said? Good for me. Nice. This is t squared. So then if you just play musical chairs, you get t squared is equal to 384, 1, 2, 3, 4, 5, 6 over 1.016 E13. Okay. So let's bust this out. And, of course, that top guy is cubed. It's cubed, of course. So then when you do this, you're going to go, oh, so 384, 1, 2, 3, 1, 2, 3, cubed, divided by 1.016 E13 is 5.57 E12 seconds. So if you divide that by 86,400, oh, God bless you, dumbass. God, you're dumb. First of all, let's try square rooting it first, okay? To the 0.5. Oh, yay. And then divide by 86,400. And lo and behold, you get about 28 days. 28 days, give or take. Yay, which is about the period of the moon. Yes? And 27 1/3, whatever. Let's don't quibble here, people. Okay. What if I put up a space shuttle up into orbit? Oh, cool. We'll do that one too, I guess. So height of the altitude, space shuttle. So it was roughly 330 miles. Let's just say 400 miles. Sure, let's say 400 miles. So let's say the space shuttle was up at 400 miles up. Okay, now 400 miles obviously needs to be converted to meters. Yes, but let's go ahead and bust that out. So 400 times 1.6 times, so 640,000 meters. 640,000 squared, not squared, cubed rather. 640,000 cubed is that nasty thing divided by 1.016 E13. And if you square root that, you get that guy. Oh, wait, that's 160. Yeah, something's a little screwy there. That's 160 seconds. That's a little wrong, Jay. It's a little wrong. Oh, I know what's wrong. I know what's wrong. We just did the altitude. We need to add that on to, let's try it again. So we need to add that on. So what we need to do is we need to find R plus H. So our H is 400 miles. So 400 miles plus the radius of the Earth in miles, radius of Earth is about 4,000 miles, isn't it? Yeah, 4,000 miles, let's say. So about 4,400 miles. 4,400 miles times 1.6 kilometers times 1,000. That would be the radius of its orbit. So because I'm an idiot, only did it as if it was only 400 miles from the Earth's surface. So that would be, or from the Earth's center. But that means it would be orbiting inside the Earth, which is ridiculous. So let's try it again. 4,400 times 1.6 times 1,000. There we go. Now we got to cube that sucker. Cubed divided by 1.016 E13. And then we need to square root that sucker. And we get about that many seconds. Yes? So if I divide by 60 seconds, I get about an hour and a half. which is what it was. I remember that back very, very distinctly back as a kid. It took about an hour and a half for the shuttle to orbit the Earth. Okay, and I always thought that was pretty cool. You can get all the way around the Earth in an hour and a half because you're hauling asses. Let's be honest. Okay, so that's pretty cool. Good times there. I think the other thing I wanted to do a couple of. Ouch. Were all right, that's enough for today. I'll make another video soon.